Welcome back to ECE 442-542. I like the volume in the classroom. We're going to actually need that in a little bit. You'll want to be getting engaged with different activities. For now, let me make some announcements. Homework 4, I'm pushing the due date ahead in time. You now have the weekend to work through that. You may have to do a little bit more outside watching or looking at notes to get that. I'm not sure how far we will get through our material today. That's why I'm extending that a little bit. One of the questions that is coming up is people are having trouble correlating their hand effort with MATLAB. The C to D, or continuous to discrete function in MATLAB, has many different parameters. In the, let's say, the third argument, you can specify a particular method for that to use in MATLAB. You can have it do the zero order hold. That's the default. If you do not specify a method for continuous to discrete conversion, I'm sort of assuming you can check your own algebra with the forward and the backward, but the bilinear is really referred to as Tustin, T-U-S-T-I-N. So you can use that to check your bilinear. There's a matched for the mapping, pole zero mapping technique, and like I said, the zero order hold is the default approach if you're using MATLAB to do your continuous to discrete conversion. That's something I hope keeps you moving forward while you're working homework number 4 so that you can meet our target deadline. Also happening on the 9th is the review session for exam number 2. That will be held in the ILC, room 150. That's different from where it was held the last time. I think our next review, I shouldn't even say, but our next review session is back where it was at the first. So we're making sure that you pay attention. I guess I do need to set up maybe a review session for the final. I know that seems like it's a long way off, but we're already halfway through the semester, essentially. Exam number 2 is a week from today in this classroom. That, I hope, surprises no one. Today we have a few goals. One is to review the numerical integration strategies or techniques that we looked at last time relative to forward, backward, and trapezoidal. Just writing those down. How do we replace the S with an expression in Z to convert these transfer functions? Then we'll spend a little time, you will spend a little time working on homework number 4, problem number 5. And that is to try to help you clarify and save time in the long run. Instead of struggling all weekend trying to do homework problem number 5, let's see if we can solve that today. And that involves using these numerical integration strategies on state space representations. Then we will summarize those state space formulas, meaning we'll look at those for different numerical integration techniques, forward, backward, and trapezoidal. We'll look at all 3 of those. We'll only derive the result associated with homework number 4, which is the backward. And then we'll move into the pole zero mapping technique. And that, I think, is problem number 4 on homework number 4. And depending on how far we get into that, I may provide you with information, notes, and videos that I've captured already or in previous semesters dealing with pole zero mapping if we don't get there, so that you can work on those between now and Monday. As a summary of what we started with, relative to these different scenarios of doing discrete equivalence. Scenario number 2 was where we were preceding our system with a zero-order hole. And that's what we started with in finding these discrete equivalents. Now we are concerned with scenario number 1, which is where we do not have a zero-order hold or any kind of hold device preceding our system, let's say capital H of S, before we want to then repackage it in a discrete time version where we are trying to convert an analog transfer function, C of S, H of S, into a discrete time transfer function, C of Z, H of Z. And there are a couple of ways that we are going to, a couple of categories for doing this. There's numerical integration, and there's pole zero mapping. And I want you to be comfortable with all of those before exam number 2. We started with the numerical integration techniques, which were concerned with finding these conversions for systems modeled or represented in the frequency domain, these H of S's to H of Z's. And we derived those and ended up really with Z expressions, expressions that had this variable Z, which is a complex frequency variable, some combination of Z's and T's that we could then just substitute in for S into our transfer function in the analog domain in order to generate the discrete equivalent. And we derived that for 3 different cases. The forward, and this was all based on trying to approximate the area in this little sliver when we were doing a numerical integration of, let's say, x of t, finding the area underneath this x of t curve. We used that picture to derive this forward approximation, which is starting at time little n minus 1 and looking forward. The backward was starting at time now n and looking backward. And the trapezoidal was using basically a linear connection between now and then, not now and later, so now and then or now and previous. And that gave us this trapezoidal approximation to this sliver. And we called that the trapezoidal technique, or it's the bilinear technique, or MATLAB calls it the Tustin. So there's a lot of different words to describe the same technique, but it's a numerical integration approach. And these are the different substitutions that you can make based on what we had derived last time. Now what we want to do is actually think about that in a time domain setting. Now suppose somebody gives you a state space representation in continuous time, and you want to maybe model that filter, that controller, that system. If we're doing scenario number 1, let's sort of focus on a controller or a filter, and you can see what inputs and outputs we are using. We're now sort of saying, suppose that we have an air signal it now goes through this system and generates an output which could be the input to our system. Is that confusing you? But beyond that U, which is the output of this system description, the input is maybe an air signal, E. This could represent our controller, this system. This might be a controller or a filter, it's not being preceded by a zero-order hold when we move it into a discrete time representation. But we want to be able to move from A, B, C, D, and you learned that maybe in pre-kindergarten. We want to go from there to phi, gamma, h, j. So we're mixing Greek and English. That's why we're now in college, right? We're speaking in two tongues in one time domain, which is the discrete time domain. But we want to now find a phi, a gamma, an h, and a j from an A, B, C, D, or in another way of saying that is to say, well, can we find phi that's some function of A, B, C, D, and T? Is there some way to find a phi matrix that's some combination of the sampling period, capital T, maybe A, maybe B, maybe C, maybe D? We want to find equations for phi, gamma, h, and j, and you now are tasked with the following. I want you to find phi, gamma, h, and j using numerical integration, but one in particular, which is the backward technique. That's your assignment for the next 10 minutes or whatever it takes. I want you to work with yourself, with somebody else, to find phi, and you can't just find them, you have to derive them. You can find them on your homework assignment if you've looked at your homework assignment. So it's not just a find, it's not a hide and seek, it's a figuring out where they went to hide. You know where phi is hiding. You know what that is based on your homework assignment, but I want you now to derive phi, gamma, h, and j using the backward rule for numerical integration. Is it clear what I'm asking you to do? All right, begin. And if you want to work with somebody, that's allowed. Here are the equations. Is that where you wanted me to scroll back up to? You're assuming you have A, B, C, and D. Just leave those as variables. And now I'm asking you to find phi, gamma, h, and j. And if you have questions, let me know. If you've already solved this, don't give your answer away right away. If you've already worked your homework assignment. If you have, you might raise your hand and get together with somebody else that's worked it and see if you worked it the same way. Do you need more time? Or do you feel like you're on the right path? How have you started, or how has somebody started this process? What are you thinking about using in transitioning or going from continuous to discrete in the time domain using the state space representation? What is somebody trying, or what are you thinking? I hope you're thinking. It's not easy. It's not necessarily easy. That's not the point. You may have to struggle. That's the idea. Because you may have something like this when you get out that you haven't really seen before, and now you have to make this jump. But what do you know? What did we do last time relative to these numerical integration techniques? I summarized those in the table, didn't I? That's what we did last time, and darn it, that's in the frequency domain. You're in the time domain. But how do you connect those? Can you somehow start your state space in the frequency domain, or can you get it into the frequency domain, and what does that require? Did anyone try to Laplace transform the state space representation? Do I see a few hands? That's a good start. That's a great start, which means that did you do something like x of s is equal to ax of s plus b, whoops, our input in this case was e, wasn't it? E of s. Did you do that? And what was, so now you Laplace transform the state equations, and you can pretty easily Laplace transform the output equation, which is the u c x of s plus d e of s. Now you have an s as a variable floating around. Hint, hint. And what did we do last time when we wanted to do this continuous to discrete in the frequency domain? We fell down. We replaced s with one of these expressions, and now we're trying to do the backward approach. There's the big hint. Now you replace s with this second row of this table as far as an expression, and you convert all of your x of s's, u of s's, and e of s's into x of z's, u of z's, and e of z's. Now can you use that to go back into the time domain eventually in the discrete setting with state space matrices? That's the hint. That's the map. Using this substitution, now that we've Laplace transformed those equations, use this. Now you're in the z domain. You now know how to go into the time domain once you have this z domain expression or equation. If you don't, you need to know by Monday and Wednesday. Monday for the homework, Wednesday for the exam. So continue. And remember, you're working with matrices and vectors, which means you can't just divide or put something in the denominator. You sometimes have to do matrix inverses if you're inverting things. You can multiply and divide by scalars. Z is a scalar. T is a scalar. T is just a number. Did you get this far? You can multiply through by scalars as much as you want, and t is just a number. That's the sample period. Z is a scalar variable. Now can you take that equation into the time domain? Because that's where we eventually want to end up. Can you put this last row into the time domain? And I will do that in real time. This shouldn't be too bad. This is now x at time n plus 1 minus x at time n equaling at x of time n plus 1 plus bt e of n plus 1. Are we finished? Probably not, huh? Darn it. Yes, question. I'm sorry. I didn't hear. I'm hard of hearing. Okay, so the question was, in our expression for capital X of S, capital E of S, and eventually capital U of S, why didn't we substitute for S there? What we are really doing is we're saying when we go from continuous to discrete, this X vector, this U vector and E vector will immediately go from S to Z. So that's not really what we have to worry about in terms of the arguments of X, U, and E. Those will just transition immediately from S to Z. We are using now S's and Z's as operators around those vectors, those transformed signals. So we are now looking at, when we go from C to D, continuous to discrete, we are going to just somewhat magically say that capital X of S as a vector is going to transition to capital X of Z as a vector. And we don't have to worry about doing the S to Z inside the argument of our signals. That's going to just take care of itself. What we are wanting to do, though, is use the S and the Z's as operators. And that allows us then to, with respect to the last blue line, say, okay, here is something that relates in the frequency domain my input, which in this example is E, and my state vector X, in terms of A, B, T, and Z. Did that help explain? So you don't have to get that far down into or trying to relate the arguments on your signal vectors or on your vectors X, E, and U. You're just using what's coming in front of those. And now you have an equation for relating in the time domain a discrete time state vector at the current time, that's little x of n. At the future time, that appears a couple of places, and the future input. What's wrong with this in terms of not immediately sort of giving us a state space representation? Do you see why this is not sort of, oh, if we just move things around a little bit, we would be done? Do you understand why that's not the case here? What do we want for a state space representation? We want this kind of structure, and how does that structure differ from this structure? I know it's not all on the same slide, I'm sorry, but I hope you can sort of remember what you saw that I circled here or highlighted in yellow. Put that in memory. How is that different from this? And I'm going to argue that there's really only sort of one main thing that's different. Pardon? E of n. E of n is not here, is it? We have e of n plus 1, darn it. That's one time step into the future. We want our state space to be x, or whatever our state vector is at the future time, one time step, equal to something times that state vector plus something else times the current input. Right now we're one time step into the future with our input. That's what's messing us up. Does everybody see that? Now we have to figure out a way of maybe getting around that. And how would you do this in a real life scenario? You might close up your book and go for a walk. You might go into the kitchen and wash your dishes. You might distract yourself. Go away from the problem so that you're not focused on this. You may want your brain to just sort of start making some random connections. And what you're trying to do is come up with a novel way or something that you're not used to seeing happening with this, because this is not what you want, is it? You somehow need to re-express this in terms of something one time step into the future, and that something is a state vector equal to a matrix, we're calling it phi, times the state vector now, plus an input matrix gamma times the input matrix now. So, unfortunately, we don't have time to go for a walk. We do, I guess, but that's not what you're paying for. So, what I'm going to do is I'm going to write these in terms of two sets. I'm going to group all of my signals that are the future time on one side and all of my signals on the present time. I don't really like to say current in an ECE class because then everybody starts thinking current and voltage. So I try to say present instead of current, but they're the same if you don't get confused with current and voltage. Let's now do what I just said. Let's isolate all of our future signals on the left, which what I'm trying to say is let's write x of n plus 1 minus at. And here another thing that might confuse you is that although those two variables look like they're capitals, are they really the same? They're a little bit different, aren't they? Why? T is a scalar, A is a matrix. It's 10 by 10. It's the elephant in the room. T is just kind of sitting there, right? Oh, I apologize for those of you that aren't seeing this lecture. You didn't get quite the elephant description. The same thing goes for B and T. B, how wide is B? Now, any answer is correct almost, because I didn't tell you, did I? I didn't tell you how many inputs you have. In this class, we usually work with one. If there's one input and 10 states, how big is B? It's 10 rows tall and 1 column wide. It's tall and thin. Capital T is still just a scalar. Now we've done what we said we were going to do, and here is the new way of thinking that may have not come to you until you'd slept on this for a few days. And you may not have time to sleep on it for a few days, so I'm going to sort of tell you how you can do this. If you go back here, there's something subtle going on between the left continuous time and the right discrete time. Can you see what that might be? Something subtle besides going from continuous to discrete. What is subtle going on in those equations? There's a W instead of an X. There's a W on the right. It's not an X. So that's actually significant. We're going to make that significant. Meaning, somehow our state variable, this variable that's internal to our input is E and our output is U. We shouldn't be messing with those. We should have the same input and the same output on continuous and discrete. So E the input and U the output should be the same. And I know this is confusing because U is usually our input, but U in this example is our output because it's the output of our controller or the output of our filter. E is the input. What we can now, thinking that way, saying, oh, we are not locked in to keeping our state vector as X. Really? Well then, let me do something magic. Let me just lump all of those signals, weighted signals, into one new vector, W of n plus 1. How tall is W relative to X? If they stood in a lineup and we took their picture, how tall would X be relative to W? They're both 6'1". They're the same height, aren't they? They're the same they're keeping track of the same information. They're not the same signals, but they have to be keeping track of the same information. W is the same dimensionally as X. If X is 6 by 1, W is 6 by 1. We've defined W. What we've done here is we've simply said, oh, let's define. We've now defined W of n plus 1 to equal X of n plus 1. If I would have written it that way, it would have been easy, right? You know they have to be compatible if they're in the same equation. One's on one side and one's on the other. This is minus AT X of n plus 1 minus BT E of n plus 1. And all of that is, in fact, equal to X of n. Really, W of n plus 1, which we will use in a little bit later, is X of n by what we had defined up above. But really what we want, maybe what I'll do, I'm going to cheat here, I apologize. I can play fast and loose. I want to locate that up there. And I can even to keep track of later. Is it okay that that's there? That's all we've done. We've just defined a new vector, w of n plus 1, and in fact, the way that we defined it, it's equal to x at n. So if we really needed to know what the state vector was that we started with, x at time n, well, that's just the new state vector w at time n plus 1. We've got x if we need it. Is that clear? That we're going to tuck in our pocket and save for later. So keep track of that. But for now, if we know w at time n plus 1 is equal to this right-hand side, what do we know w at time n equals? And this one is so easy, it's maybe hard. It's not hard at all. You've got w at time n plus 1 defined in terms of other things. Just change the argument by 1 up above and you'll have w of n. Let's do that. We now know that w of n is equal to x at n minus at x of n minus bt e of n. Is everyone comfortable with that? If it equals, if that red equation is true at time n plus 1, it has to be true at time n. That relationship of x, w, and e. Well, I can combine some of these terms. That's not a big stretch. But now, can I solve for little x of n? Sure. Let me isolate x of n by itself, and I'm going to do that by pre-multiplying on the left every term by what's multiplying x now, or the inverse of what's multiplying x now. Meaning, I'm going to now write that x of n is equal to I minus at inverse w of n. And if I put the e on the same side as the w, that bt would have a plus sign, whoops, and it needs to be pre-multiplied also by I minus at inverse. Is it clear where that came from? Yes. I'm sorry? Good question. The question is it always invertible? Sure. Now, why can I say that? It may not be, but it should be. I is always full rank. It's just ones on the diagonal. If you make capital T small enough, what's going to happen? Well, you're not going to change I very much, and so you're really inverting the identity matrix, roughly. So it's pretty good to assume that this matrix always has an inverse, but that's an excellent question. Because what would happen? You get out on your job interview and somebody would give you this matrix and they would say, give me the backward rule numerical integration approximation from going continuous to discrete. You should have heard me last night trying to explain this lecture to my wife. That went over like a lead balloon. A lot of jargon. We're using a lot of jargon, but the ideas are the same as to what you might do in some other classroom. as far as this process, right? Where was I? Inverting. Do you see why that's okay? I minus AT. You can sort of think this through. I is easy to invert. If I gave you that on the final, to invert I, please get the right answer, right? It's just I. And you could thank me on your way out with the exam, right? So, now we have x of n. And I'm going to go back to what I said. Let's remember what we needed for later. We want a state space equation that has w at time step n plus 1 equal to something on the right that's a matrix times w at n plus another matrix times the input at n. And we now know that w of n plus 1 is equal to x of n. Well, we don't want x of n on that side because that would be messing up or mixing x's and w's. That's not what we want. We only want to mix w's with w's and e's. Yay! We have that, don't we? Meaning, now we have a way of writing w of n plus 1 is equal to x of n, which is I minus AT inverse w of n plus I minus AT inverse BT E of n, and voila. What we have done is this is our phi. There's our gamma. And I will leave it to you to figure out what h and j are. But that's a linear equation. You know u is equal to some linear combination of, it's cx plus d e, and you know what x is in terms of w and e. You're done. Didn't I save you a little time on your homework? I just solved homework problem 5 for you. You guys helped me. Okay? Is it clear what we've done? Now you know how to approximate. If somebody gives you A, B, C, and D in the continuous time system, you now have a way of simulating that with Excel or MATLAB or your hand, because this is now just a difference equation. This is a coupled set of linear difference equations, even if A is 10 by 10. This isn't that hard. You no longer have to integrate. You just multiply and add, and you now have a way of filtering or controlling signals between the input E and the output U. Questions on that? This is what you can do if you do it for the different strategies. We did the middle, we did the backward column for phi, gamma, h, and j. I'm giving you the answer, but I gave it to you on the homework anyway. If you did this same process for the forward and the trapezoidal, the forward is not hard at all. You don't even have to introduce this new w. You can keep the x. The trapezoidal is a little more interesting, and I think I'll post that lecture and notes online for you and won't make you sit through that next time. Okay? Now what I want to do, is that a hand or just stretch? I need to stretch too, because we're going to stretch into the next discrete equivalent approach. Are we ready to move on? I had a history professor, and he would lecture for an hour and a half like this. It really bothered me, but I think his desk, well, maybe it was about this same height. He would just stand there and give us history. Right after lunch, I, yeah, I tried to stay awake. I did most of the time. That's about all I did was stay awake. All right, let's move into the next topic. I don't know where that came from, but I apologize. Let's now move into pole zero mapping, because this is problem 4 on homework 4. The idea is really sort of a 3-step process. The first step is to map poles of h of s to poles of h of z. And the first 2 steps you could interchange. You just need to find the poles in h of s and the zeros. You really factor the transfer function into pole factors and zero factors, and then you'll factor out a constant in the numerator. Then you map poles to poles, zeros to zeros, and then we have to match gains of h of s and h of z. Does that make sense, what I'm saying there? Gains. H of s can be a lot of different things. If it's a low-pass filter, what do you know is happening at low frequencies? Or if I said sketch the Bode plot of a low-pass filter, do you see the image if you had to sketch the magnitude of a low-pass filter? A Bode plot magnitude for a low-pass filter? Do you see that? Can we just draw it? It's flat, and then it starts rolling off, doesn't it? It's flat and rolls off. Where would we match the gain? Probably where it's flat. And where would be a convenient space or location? Maybe at low frequencies, really low frequencies at DC. We might match the gains of h of s at DC with the gain of h of z at DC, which means we would evaluate h of s where? We want the DC gain of h of s if it's low pass in behavior. What is it? DC gain, s equals 0. What about z in h of z? Z equal 1. So now you would evaluate h of s at 0, get a number, because you know the gain. You might not know the gain in h of z. It might be some k, and that's what you're trying to solve for. But you know all the poles and zeros after steps 1 and 2. You're mapping through this relationship, z is equal to e to the st. Let's walk through this in a little bit more detail. Here's the approach. Somewhere, let's go back. And in this approach, I may throw in some examples so that you see what we're doing as we go. First, as I said, we factor the given transfer function, h of s, into pole and zero factors. Then we start with that 3-step process that I had before. First, we'll map the poles of the continuous time transfer function, h of s, to corresponding pole locations in the z-plane, so to z-plane poles, using z is equal to e to the st. As an example, suppose that I had that. That's about as trivial of an example as I can give you. Where's the pole? Is that system stable? Yes, the pole's in the left half plane. That's really just a low-pass filter, isn't it? Maybe you don't like the DC gain. What is the DC gain of that low-pass filter? 1 over A. May be fine, may not be. That's not what we're interested in. We want to map the pole, and the pole is in the S-plane at minus A. We now know that we have S is equal to minus A. We map that through this relationship, Z is equal to E to the ST. We now know that where the pole in the Z-plane needs to be, the pole in the Z-plane needs to be at Z equal to E to the S, which is minus A times capital T. We will have had to determine what capital T is, and once we do, and if we're given A as a number, that E to the minus AT is just a number. And where is that located? E to the minus 6 times 0.007. That's less than 1, isn't it? That's inside the unit circle. That's a good spot. Now, if we know that we want to pole there, what's the factor going to look like in the denominator of our approximation, of our discrete equivalent? If we know we have a pole located at Z equal to E to the minus AT, what factor do we need to introduce into our transfer function, capital H of Z, to accommodate a pole at that location? What factor did we have in the or in the continuous time? We had a factor of S plus A. And that produced a pole at S equal minus A. We now want a pole at E to the minus AT. We then want a factor like that. And if it's downstairs, since it's a pole, I'll just put that there to keep it there. Is everyone clear with that? That minus 1 is just because it's downstairs. That's how we map finite poles in the S-plane to those poles in the Z-plane. Now we do the same thing, or something similar, with our finite zeros. We map our finite zeros of H of S to Z-plane zeros using exactly the same relationship or mapping between S and Z. For example, suppose we had some numerator that was maybe K S plus B. And let's not worry so much about the gain. What zero factor would we need to have in the numerator of capital H of Z to be consistent with this S plus B factor in our continuous time H of S? Is that okay? That's now the factor. We're not going to worry so much about the K. Maybe I would just say a K bar if you're getting nervous about that. That's now our poles and zeros, but the thing I'm not really finished with are the zeros, because we actually have these objects called infinite zeros that we have to worry about. Infinite zeros of H of S, and here let me just say this parenthetically, are typically mapped to zeros at the point in the z-plane, z is equal to -1. That's sort of this little twist on this pole zero mapping. That's supposed to be the top half of the unit circle. This is the z-plane. And if we looked at z is equal to e to the st, and we wanted to look at the frequency response, we would replace s with j omega. And with that replacement, this point in the z-plane is like infinity. Meaning, if we have z is equal to e to the st, and somebody says, I want the frequency response in the z-plane. Well, we know what the frequency response in the s-plane is. That's when we look at the imaginary axis in the s-plane. We replace s with j omega. If we do that here, what do we have? That's just a polar number, isn't it? Or a complex number which has a magnitude and an angle. It's the magnitude of e to the j omega t and the angle of e to the j omega t, and those two are pretty clean to find. If you found the magnitude of e to the j omega t, if you used Euler, you would say, oh, that's e to the j omega t is cosine omega t plus j sine omega t. What's the magnitude of that? Cosine squared plus sine squared. Now we remember our joke. Well, maybe you don't, but I'm not going to go there. But for those of you that had 320 with me, yes, no, did I tell you a joke about sine squared and cosine squared? Don't tell me you've forgotten. We'll talk about that offline. But you should be able to convince yourself that the magnitude of e to the j omega t is 1. And the angle of e to the j omega t, if you simply took the inverse tangent of the sine omega t over cosine omega t, that's just going to be the angle of omega t. And what's that going to do as we make omega really, really big? Well, as far as it can go is 180. It can only go to -1 at 108. I'm sorry, it can only go to 1 at 180 in the z-plane. And it starts wrapping around. So really there's only, that's why the -1 looks like infinity. Now, with that sort of stated, we need to map infinite zeros in h of s to factors that give us 0 when z is equal to -1. In other words, the 0 factor associated with z equal to -1, what does that factor look like? If we want that factor to disappear when we set z equal to -1 in that factor, what's that factor going to look like? Is it clear what I'm trying to say? We want a factor such that when we replace z with -1 it becomes 0. If I put z equal to -1 in that expression, it's going to vanish. That means however many zeros at infinity you have in h of s, you put in that many factors of z plus 1, typically. And we may talk about the other cases the next time, but for your homework, just assume that you can substitute that many z plus 1 factors into your expression. Let's see what that means or looks like here. We've already looked at an example that's similar or that really has what we want. Suppose we have that factor, and I ask, what's the pole 0 excess? That's kind of a new phrase maybe for those of you that didn't take an earlier controls class like 441. But how many more poles do you have than zeros? And when I say 0 here, I'm meaning finite zeros. You now have some poles and you have some finite zeros. How many more poles? What's the pole 0 excess in this expression? 1, isn't it? We have 1 pole and no finite zeros. The pole 0 excess is 1. That actually tells you how many zeros you have at infinity. Therefore, you have 1 0 at infinity, which means in your discrete equivalent, when you want to produce an h of z, you need a 0 when z is equal to -1. And we know how to produce that. That is, we need this factor in the numerator expression, which now means that we have a k bar z plus 1, and we already know what the denominator looks like. That was this z minus e to the minus at. Meaning each infinite 0, if you had 2 zeros at infinity, you would put z plus 1 quantity squared in the numerator. Each infinite 0 places a z plus 1 factor in the numerator of capital H of z. We're almost finished. What we don't have is k bar. And we get that, or we find that by step 5, which is to adjust or select the gain of h of z to match the gain of h of s. And this is not match.com. It means we don't have a perfect match. We have a match at one frequency. So if you're on match.com, you can say, I only want to match at one frequency. I have no idea what I'm talking about. But if you have a low-pass behavior, for example, in your transfer function for h of s, you know that its magnitude looks something like that. if it's low pass. Let's say that's the magnitude of h of j omega. You would then take this point, which you could find by saying h of 0, and that would give you a number for h of s at s equals 0. You would use that to match h of z when z is equal to 1, the DC value. What about the high pass? So this now says that you would take h of s at s equals 0 and set that equal to h of z when z is equal to 1. What if you had a high pass? What's the magnitude look like there? Something like that. Now you might be interested in that frequency to match that, so that now you have h of s as s goes off to infinity equaling h of z when z is equal to -1. Now you have enough to do homework number 4. Thank you for being patient and giving me an extra minute. Hopefully I saved you more than that on your homework, but your homework is not due Friday, it's due Monday. So if you finish it on Friday, study over the weekend. We do have a review session on Monday.